Horan, who will speak about fast quantum algorithms for solving multivariate quadratic equations. Let me just add, I'm very, very happy to have Kelsey. She was my student twice in an undergrad class and a grad class when she was an undergrad. And I'm very, very happy to see her doing so well. Also, we're going to take Kelsey out for dinner in the usual place, Evelyn at New Brunswick. If you'd like to join us, please let me know immediately after the talk. It's 6:45 at Evelyn. I'll be standing right here, and just let me know when you can make it.
Hi, I'd like to thank Professor Zalberger and Lisa Carbone and my advisor, Dan. I'm presenting fast quantum algorithms for solving multivariate quadratic equations. My collaborators are Jean-Charles Forget and Ludovic Perret from University Sorbonne in Paris, and Mark Kaplan and Alham Kashepi, who are part of the University of Edinburgh. So, should I click here? Okay, so we all know that quantum computers are going to change the way that we think about security, cryptographic security. The quantum algorithms that are coming out are very drastic and will change the way that we think of computation. So Peter Shor's algorithm came out in 1994, which showed that in quantum computer can factor large numbers in polynomial time, which basically makes RSA one of the most standard cryptographic protocol, not very good, not as secure. And other quantum algorithms are coming out, such as Grover's algorithm, which can decide any problem in NP in time 2 to the n over 2, if it was 2 to the n classical computation time. So the question is, what exactly are we supposed to do about this? What can quantum computers do? And it's time to determine the level of security that we can expect from our classical cryptographic setups when quantum computers come around, or if, as Professor Zalberger was saying earlier. So the NSA came out with a call for proposals for post-quantum secure cryptographic algorithms. So they want to transition to quantum-resistant algorithms. So when a quantum computer comes out, they want to make sure that we can keep our level of happiness, our level of security. This is the NIST competition. The announcement was August 2015, and all proposals were due, I think it was November of last year. The first meeting of everyone who's proposing is in April. So we need to develop quantum cryptanalysis against post-quantum cryptosystems. There are a lot of supposed post-quantum secure cryptosystems. The question is, how secure are they? And in terms of security measures that we know, what's the quantum bit security of these algorithms is the question. So this talk considers the quantum security of the problem of solving a boolean multivariate quadratic equation, a system of equations. We give a Las Vegas quantum algorithm for solving, which solves in, okay, this isn't really going to work, 2 to the 0.462 n quantum gates. And if you know much about Grover's algorithm, you would expect 2 to the n over 2, so this beats that, which is very nice. And to our knowledge, this is the fastest algorithm for solving the multivariate quadratic problem. So first I give some background, and then...
But don't you want it to be slow for security? So fast is bad.
So it's, we're giving the fastest algorithm that we can think of to break the crypto system.
So you want to brag, you're hackers.
I guess, yeah. So we can recommend, okay, well, if you want us to not be able to break it, these are the parameters that you should use. This is the number of variables you should have in your polynomial ring. Is the last slide, actually. First I go over some background, and then I go over the classical algorithm, a little bit of background on quantum computation and overview, and Grover's algorithm specifically. which then I can go over the quantum algorithm and give a bit of complexity analysis for it. So the first problem that I'll present is polynomial system solving over a finite field. Given a set of polynomials over a finite field in n variables, the problem is to determine a common zero. A problem is a multivariate quadratic problem, which is basically the same, except we have over f2, and the maximum degree of any polynomial is 2. And the goal is still to find a common zero of these polynomials. The important thing about the multivariate quadratic problem is that it's NP-hard. And a lot of the post-quantum cryptosystems that have been proposed for the NIST standardization process their security can be found to rely on this problem. So multivariate primitives, code-based primitives, and lattice-based primitives all have some type of security that's related to this. In terms of the classical complexity, we have exhaustive search, which is brute force basically, and fast exhaustive search is order of 2 to the n binary operations with fast polynomial evaluation at 4 log n for the polynomial factor. The second algorithm is an approximation algorithm, which came out in 2017, and that algorithm attempts to, it approximates all of your lower degree polynomials with one high degree polynomial, and then provides a probabilistic method to find a zero of that polynomial.
Wait. What exactly, MQ2, you're given a finite set of polynomials in a polynomial ring over F2 with a finite number of generators.
Over F2.
Over F2. And you're trying to
find a common zero of all of them.
Okay. So it's not completely find all of them, you just have to find one.
So our algorithm finds all of them, but I guess the problem is to find one.
Okay. Is there a difference in, is finding all of them slower, or is it roughly the same as what you would do if you just were trying to find one?
It's roughly the same.
Okay.
But it does depend on how many solutions you have.
Okay.
If almost everything is a solution, then obviously it's different. But depending upon the construction, if you have a hard instance of the problem, it's the same.
You want to do a point-like solution? I mean, it's algebraic geometry or a finite field, but you want them to be points instead of sub-varieties?
It's an element of the variety. You're looking for an element of the variety. Okay, so the second algorithm is 2 to the 0.8765n. And then the third one are hybrid approaches, which are based on Grosvenor basis techniques. I'll go into this further in the classical algorithm because this is what we quantize. But this is the best algorithm these are the best algorithms that we know of for solving the multivariate quadratic problem. In terms of the quantum complexity, there's quantum exhaustive search, which is a straightforward application of Grover's algorithm, which I'll explain later. The second one are quantum hybrid approaches, which are a quantized version of the hybrid approaches based on Grover techniques. There are 2 papers that came out with this. The first one doesn't provide an asymptotic complexity for comparison. And the second one is called Grover XL, which has very similar techniques to what we do, but in the end, one of our subroutines is probabilistic, so we achieve a better quantum, better and faster algorithm. I guess faster is the best word. And then there's an HHL variant. I'm not sure who's familiar with HHL, but this is a quantum algorithm for solving a linear system of equations. And this algorithm constructs a Macaulay matrix and uses HHL to solve this linear system of equations. So the complexity is given below. The complexity directly relies on this kappa here, which is a function of n, but we don't know the behavior of n.
I don't suppose the paper, footnote 7, contains any experimental or data on kappa, on how it behaves.
They don't analyze the asymptotic complexity in terms of its relation to systems of equations. Yes.
Sorry, what is kappa the condition number of?
Kappa is the condition number of the matrix that you're using to describe the linear system of equations.
So you just hope it's good.
Yeah, I think that they just hope it's good. But we don't directly compare our results to this. That's part of an extension, hopefully, at some point. I'm just giving all of the options that we have. So the theoretical computational bounds in terms of quantum complexity of the MQ2 problem is it's lower bounded and upper bounded. We have an upper bound using Grover's algorithm, which can decide any problem in MP in 2 to the n over 2. And we give an algorithm that beats that, so, which takes advantage of the problem structure. So I present the classical algorithm first, and I go over, there are 3 steps to the algorithm. The first step is specialization of a subset of variables. So if we have, I hope that it can be seen, there are n variables along the bottom. Each can take on a value of 0 or 1. And we specialize the last k variables. So we assign an actual value to these and leave the first n minus k variables as variables for all m equations.
Wait, each row is one equation.
Yes.
But these variables, these are not, you're not messing with the coefficients.
No.
You're just plugging in different, okay.
Yeah.
Okay.
It's a partial evaluation.
Okay.
So you can see here, you evaluate the system on this specialization, which is the A1 to AK, the specific values that you're fixing for this round of the algorithm. And so you'd like to check the consistency of this system. If it's consistent, you have a potential solution that ends with these last k variables. So then you can exhaustive search on the remaining n minus k variables to determine the remainder of the solution. With the use of Macaulay matrices, we can reduce the multivariate quadratic problem to the problem of solving a linear system of equations. So when we specialize a system, we can construct a Macaulay matrix and check the consistency of that. So now a Macaulay matrix is, the formal definition is here. I give an example in the following slide. The columns of the Macaulay matrix are monomials up to some bounded degree in your polynomial ring. And the rows correspond to multiples of each polynomial in your system up to the degree. So it's clearer here. If F is the system of equations, and A, C, B, D are all elements of F2, or FQ in this case, then the columns are all monomials up to degree bound 3. And the rows are multiples of each of the polynomials up to that same degree bound. So you can see that there are more multiples of F3 because F3 has degree 1, whereas the top one, there are less. And the entries are the coefficients of the corresponding monomial in the multiplied. So this is a linear system of equations. The key property of the Macaulay matrix is that if the system has a solution, this U, M equals, we'll call this vector R, then the original system doesn't have a solution. Because this would imply that 1 is in the ideal generated by the system of equations and the field equations. So we have our linear system here, and the problem is to solve it, to check the consistency, not to solve it. First, we put some bounds on the dimensions of the Macaulay matrices in order to analyze the complexity later. The number of columns is basically the number of monomials up to the degree bound, D. The number of rows is the number of monomials times the number of equations by construction. And the sparsity takes into account the field equation, but is still, everything's on the order of n choose D, so. Yeah.
Is the sparsity exactly the number of non-zero entries, or is it something more sophisticated, or some kind of ratio?
It's the number of non-zero entries.
Okay.
So we want to know how big the matrices get. The witness degree is the degree D that we need to construct the Macaulay matrices in order to check the consistency of the system of equations. So the witness degree is the degree where any polynomial in a minimal Grosvenor basis can be written as a linear combination of the columns, of the rows of the Macaulay matrix. So in general, when you have a Macaulay matrix of degree, witness degree, then you can pretty much guarantee that if one is in the ideal generated by the system of equations, then the system will be consistent. And this is the formal definition, which I'll just leave here for a second in case you'd like to look at it. Yeah?
Or is there guaranteed to be a finite witness degree?
Yes. So the witness degree can be explicitly computed using the Hilbert series, which is the closed form formula for the witness degree, which was sort of the idea of the bounds. So now that we can compute the witness degree, we know the dimensions of the polynomials and everything, I can give the classical algorithm. The classical Boolean solve takes as input a system of m equations over the f2 with n variables, and outputs all Boolean solutions. This is the pseudocode for the algorithm. As you can see, first we compute the witness degree, and then for every possible specialization of the last k variables, we specialize the system, construct the Macaulay matrix, check the consistency, and then if necessary, exhaust the image. And then return the solutions that we got. So how often do we actually have to compute the second exhaustive search? Because we're sort of hoping that we can save time, right? So the question is, do we actually save time? How often do we have to check these n minus k variables? And the answer is not too often. In terms of gamma-strong semi-regularity, which is defined in the following slide, as long as we have a gamma-strong semi-regular system, we have a guarantee that we don't have to check too often. And so here we say that a system is gamma-strong semi-regular if the number of times that we have to check the remaining n minus k variables is upper bounded by the computation time of the consistency check. So it says, okay, well, this is the number of times that we're wrong about the witness degree, the number of times that we check and we don't actually have a solution in the remaining n minus k variables. Any questions so far? No? Okay, great. So in terms of the classical Boolean solve, we have a deterministic and probabilistic variant. The complexities are given here, but basically, as you can see, it's 2 to something times n. Here, gamma, all of the parameters are defined, but the important part is that in the deterministic variant, there's a theta that's present in the equation, and that's the linear algebra constant, which is the complexity of multiplying two matrices of dimension n. So we have a lower bound on that, which is 2, and an upper bound on that, which is 3. And right now we're at 2.376, and hopefully getting better. So, so you can see the deterministic variant directly multiplies these matrices. The probabilistic variant takes advantage of probabilistic subroutines, which allow us to minimize the linear algebra constant. And we always have a 2 there for probabilistic variant. Which is nice. So in terms of actual concrete complexities, for parameters alpha, if we assume alpha is 1, if the linear algebra constant is 3, so that's like grade school matrix multiplication, you can obtain 2 to the 0.8 something n in the exponent. And if you have theta equals 2, which is matrix multiplication that we don't know about yet, then you can have 2 to the 0.7 something n in the exponent. And that's shown here. So classical Boolean solve does solve the multivariate quadratic problem. And the deterministic variant has this complexity, and the probabilistic variant has 2 to the 0.792 n. This is having some assumptions on a semi-regularity of the system, but these assumptions aren't very strong. Most systems are appropriately semi-regular. Okay. So now I'll overview a bit of quantum computation from Grover's algorithm, and then we can get to the quantum part. So, in a quantum computer, you replace bits with qubits, which can be thought of as vectors. So you can see that these basis states, the 0 qubit is 1, 0, and the 1 qubit is 0, 1. They can be combined. So you have these, which are 4-dimensional vectors, which is equivalent to having 4 different basis states of like a 4-dimensional space. And any state that a computer is in is a qubit state and can be shown as a linear superposition of the basis states. So the state psi is alpha times the state 0 and beta times the state 1, where alpha and beta are complex numbers. And the probability, when you measure this state, the probability of measuring 0 is alpha squared. And the probability of measuring 1 is beta squared. So that can be seen here in this Bell state. We have a superposition of states. The first state is 0, 0, and the second state is 1, 1. And the probability of measuring either state when you measure the Bell state is 1/2. Qubits can be entangled, but the important part for this is that you need to reverse all of your computation in order to make sure that the bits that you're measuring at the end of your computation are not entangled. So that's the important part here. And any operation done on a quantum computer can be defined by a unitary matrix, which are basically rotations. And all of the computations can be performed by a sequence of gates. And I have examples of quantum gates here. You can see the name of the gate, and in parentheses there's the classical equivalent, x and naught, c naught to Foley, and n qubit to Foley. Now this n qubit to Foley is what we use. I'm just showing that there are some other things that you can do. Yes?
You have in the half-cycle bracket, just understanding the communication. If it's not a 0 or a 1, is that, what does that mean? Is that, let's say it's alpha in the bracket, is that alpha times the 1 bit?
I'm sorry, what?
What does it mean to have when you're writing, let's say bracket x, right? What does that mean if it's not 0 or 1? What's 1 plus x?
1 plus x, that's the exclusive OR between 1 and x.
Okay.
So it just computes not. If we're working with 0, 1, then it would be, flips the...
Yeah, okay.
I thought these were superpositions. You're in a
So
workspace.
the linear superposition is for the coefficients outside of the bracket notation, right? Inside it's all zeros and ones, and so you just do classical binary operations.
Okay. So that we're just picking a basis for help.
So the problem that we're working on solving, that Grover's algorithm works on solving, is database search. Given a function from bit strings of length n to 0, 1, the question is to find an input that brings the function to 1. it's presented where there's a unique solution, but there can be multiple. It's a very similar computation. So in terms of classical techniques, we have 2 to the n for database search, which is brute force. For Grover's quantum algorithm, you get 2 to the n over 2. As long as you have a quantum circuit that evaluates the function f. So I'll go over that in a second. Where we're heading with this is that we'll construct a quantum circuit and then use Grover. So Grover's algorithm uses 2 unitary operations. The first one is a sign flip. So you can see we go from a uniform superposition to a nearly uniform superposition, except the coefficient on this x star that we're looking for is negative. And then there's a diffusion operator, which rotates the state around the average amplitude of the superpositions. It becomes more clear in the following slide. After you do this multiple times, you perform amplitude amplification. And you reach a state where, with very high probability, when you measure the state of the quantum computer, you'll get the x star that you're looking for. So you can see here, this is a pictorial representation of Grover's algorithm, where you have along the y-axis the amplitudes, and along the x-axis are all binary strings of length n. And colored in the light blue is the x star that you're looking for. And the red is the mean amplitude. So the first operation takes you from the first picture to the second picture, where it just flips the amplitude of the x star that you're looking for. And the second operation rotates around the red line, the mean. So you can see doing this multiple times, you converge to a state that you want. The complexity of amplitude amplification is this. This is how many times you need to compute Grover's algorithm. So the inverse on the bottom is basically how many x stars you're looking for. In order to perform Grover's algorithm, we need to have a quantum circuit for f. So that's what we'll construct, a quantum circuit, which checks consistency of Macaulay matrices. And that's what quantum Boolean solve will be. So now for a quantum Boolean solve, we construct a quantum circuit. When we recall classical Boolean solve, there are 2 exhaustive searches. The first one is over the last k variables. The second one is over the first n minus k variables. So from the presentation of Grover, it's very nice to use Grover to speed up the second exhaustive search, but the more interesting part is to use Grover to speed up the first exhaustive search. So when we quantize the consistency check on Macaulay matrices, we want a quantum circuit which returns 1 when the system is inconsistent. Because we're looking for the A's that give the specialized system that the Macaulay matrix is inconsistent. So as a subroutine in the classical consistency check is Sparse linear system solver, which takes the Macaulay matrix and the vector R, and a subset of the field, or since we're working over F2, is a field extension for random selection. And outputs either a solution or a certificate of inconsistency. And we don't need the solution, we just need that there is one. And the complexity is given in terms of calls to the black box algorithm for matrix vector multiplication. So the significant operations performed by Sparse linear system solver are matrix multiplication. And it's sufficient to show that these operations can be executed in comparable time with a quantum circuit. So then we can say that we can count the number of gates, and as long as it's comparable to the classical complexity in the black box